Welcome back, everyone, to another deep dive. It's always amazing to me how a seemingly simple idea can lead you down these rabbit holes of complexity when you really start digging in. And today's topic is a perfect example, the Collatz conjecture.
Oh, yeah, this one's a real head scratcher. You start with a positive integer, a whole number, and then there's this really basic rule you apply over and over again. It's all about whether the number is even or odd.
Right, so if the number is even, you just divide it by 2. Simple enough. But if the number is odd, that's when you multiply it by 3 and add 1. And then you take that new number and you apply the same rule again, and you just keep going and going. And the big question is, will you always eventually hit the number 1?
It sounds so simple, right? I mean, divide by 2, multiply by 3, and add 1 basic arithmetic grade school stuff. But this thing has been baffling mathematicians for decades. It was first proposed way back in 1937 by Lothar Collatz, hence the name, and it's still unsolved.
That's what makes it so fascinating. This simple question that anyone can understand has some of the brightest minds in math stumped. It's like this little puzzle that refuses to be solved.
And it's not just mathematicians who are drawn to it. Because of its simplicity, it has kind of caught the imagination of a lot of people, even those who aren't necessarily math experts. It's easy to play around with, try different numbers, see what happens. It even has these sort of fun nicknames like the hailstone sequence or hailstone numbers.
Yeah, I've heard that one. It's because the numbers in the sequence tend to bounce up and down, like hailstones in a storm. Some even call them wondrous numbers, which I think captures that sense of mystery and unexpected behavior.
Definitely wondrous. And its difficulty hasn't gone unnoticed by some of the big names in math. Paul Erdős, a real giant in the field, once said something like, "Mathematics may not be ready for such problems." Kind of a humbling thought, isn't it?
A bit intimidating, yeah. And more recently, in 2010, Jeffrey Legarius called it an extraordinarily difficult problem, completely out of reach of present-day mathematics. So, we're not talking about some trivial little puzzle here.
Not at all, and that's precisely why we're doing a deep dive on it today. We're going to unpack what makes the Collatz conjecture so hard to crack and look at what progress has been made even without a complete solution.
Exactly. So for all of you joining us on this mathematical adventure, let's start by getting those rules super clear. We've mentioned them, but it's always good to reiterate. We pick a starting number, any positive integer, and we call it n.
Right. And then we just apply the rule. If n is even, we divide it by 2. If n is odd, we multiply by 3 and add 1. And then we rinse and repeat with the new number we get. It's like a mathematical dance, just following this simple choreography.
It's almost hypnotic in its simplicity. And mathematicians even have a more formal way of writing this rule using a function. They often call it fn. So if n is even, meaning if you divide n by 2 and there's no remainder, then fn is just n divided by 2.
But if n is odd, meaning you divide n by 2 and there's a remainder of 1, then fn is 3 times n plus 1. And this function notation just makes it a bit cleaner and more compact when you're writing things out mathematically.
It's like a shorthand for mathematicians.
Yeah.
But no matter how you write it, the Collatz conjecture essentially says that no matter what positive integer you start with, if you keep applying this rule, you will eventually reach the number 1.
And there are a couple of related ideas that mathematicians use when talking about Collatz sequences. One is the idea of stopping time. It's the first point in the sequence where the number drops below the original starting number.
Right. So it's like the first dip below the initial value.
Exactly. And then there's total stopping time, which is the total number of steps it takes to get all the way down to 1. The Collatz conjecture basically says that this total stopping time is always finite, meaning you'll always reach 1 eventually, no matter what number you start with.
So it's about whether the sequence will always eventually land on 1. And I think it's interesting that mathematicians sometimes use a sort of shortcut version of the Collatz function.
Oh yeah, the shortcut. Well, think about it. If you have an odd number and you apply the rule, you multiply by 3 and add 1, the result of that is always going to be an even number, right?
Right, because in odd times, an odd is always odd, and then plus 1 makes it even.
Exactly. So the very next step after multiplying by 3 and adding 1 for an odd number is always going to be dividing by 2. So the shortcut just combines those 2 steps into 1. If n is odd, instead of doing 3n plus 1 and then dividing by 2, you just do 3n plus 1 divided by 2 all at once.
So it's like streamlining the process a bit.
Exactly, and it doesn't change the fundamental question of whether you reach 1, but it can make the sequences appear shorter, and it does affect those stopping times we were talking about.
Okay, so now that we're all clear on the rules, let's see this thing in action. What do these Collatz sequences actually look like when we start playing with numbers?
Let's pick a simple one, say 12. We start with 12, it's even, so we divide by 2 and we get 6. 6 is even, divide by 2 again, we get 3.
Okay, so 12, 6, 3.
No, 3 is odd, so we multiply by 3, that's 9, plus 1 is 10. 10 is even, divide by 2, we get 5. 5 is odd, multiply by 3, 15, plus 1 is 16.
So the sequence is getting a bit longer, but we're at 16 now.
Right, and from 16, it's all downhill from there. 16 becomes 8, 8 becomes 4, 4 becomes 2, and 2 becomes 1. So, starting with 12, we got to 1 in just 9 steps.
9 steps, not bad. But I'm guessing the sequences can get a lot longer and more unpredictable depending on where you start.
Oh, absolutely. Let's try a slightly larger starting number like 19. So 19 is odd. 3 times 19 is 57, plus 1 is 58. 58 is even, so divide by 2, we get 29.
Okay, I'm following so far.
29 is odd, so multiply by 3, that's 87, plus 1 is 88. Then 88 becomes 44, then 22, then 11. 11's odd, multiply by 3, 33, plus 1 is 34. 34 becomes 17.
So it's bouncing around a bit.
It is. 17 is odd. 3 times 17 is 51, plus 1 is 52. 52 becomes 26, then 13. 13 is odd. 3 times 13 is 39, plus 1 is 40.
We're at 40 now.
And from 40, it goes to 20, then 10, then 5. 5 is odd, so 3 times 5 is 15, plus 1 is 16. And now we're back on familiar ground. 16 to 8, 8 to 4, 4 to 2, and 2 to 1. Whew! That one took a bit longer.
Quite a journey. How many steps was that in total?
21 steps for that one, starting with just 19.
It's amazing how much longer that sequence was compared to starting with 12.
Mm.
And I know there's at least one number that's famous for producing a really long and chaotic sequence.
Ah, you must be thinking of 27. That one's a real roller coaster ride. It starts innocently enough. 27 goes to 82, then 41, and then it just starts climbing, going way up to over 9,000 before it finally decides to head back down to 1.
Over 9,000. That's a huge jump for something that seems so simple.
I know, right? And the total number of steps for 27 to reach 1 is a whopping 111. It's a prime example of how unpredictable these sequences can be, even for relatively small starting numbers.
So we see a few examples firsthand, but obviously mathematicians haven't just tested a few numbers like we did. They've thrown some serious computing power at this problem, haven't they?
Oh, absolutely. The Collatz conjecture has been computationally verified for a mind-bogglingly huge number of starting values. As of the latest checks, it has been confirmed for all starting positive integers, all the way up to 2.95 times 10 to the power of 20.
Okay, now that's a number I can't even begin to comprehend. So with all that computing power and no counterexamples found, are we getting close to actually proving the conjecture?
Well, it's tempting to think so, right? I mean, that's a lot of numbers to check, and not a single one broke the rule. But here's the thing about mathematical proofs. Computational verification, while incredibly useful and suggestive, is not the same as a formal proof.
Right, it's evidence, but not proof.
Exactly. Just because we haven't found a counterexample yet doesn't mean one doesn't exist somewhere out there in the vast expanse of numbers. There are historical examples of mathematical conjectures that were thought to be true based on lots of computational evidence, but were later proven false when someone finally found that one elusive counterexample.
So it's a reminder that mathematical truth is a tricky thing to pin down. So if just crunching numbers isn't enough, what are some of the other ways mathematicians have tried to approach the Collatz conjecture?
Well, visualizations can be really helpful. One way to think about it is by creating a directed graph. You can imagine all the positive integers, and then you draw arrows showing how each number transforms into the next one according to the Collatz rule.
So it's like mapping out the paths these numbers take under the Collatz rule.
Exactly. And what's interesting is that for all the numbers that have been explored this way, all of these paths seem to converge on this little cycle that involves the numbers 1, 2, and 4. It's like 1 goes to 4, 4 goes to 2, and 2 goes back to 1.
Like a little whirlpool that everything gets sucked into?
Exactly. Another cool visualization is to plot the highest number reached during the Collatz sequence for different starting numbers. When you look at these plots, you see a lot of variation. Some starting numbers have pretty tame sequences, but others, like our friend 27, just shoot way up before coming back down.
So you can really see the hailstone effect in those plots.
You definitely can. And I think it's those peaks and valleys that might hold some clues about the overall behavior of the Collatz system. There's also this really interesting visualization called the Collatz tree.
I've heard of that one. Tell us more about it.
So imagine you take all the numbers that reach 1 within a certain number of steps, say fewer than 20 steps, and then you try to trace their paths backward, reversing the Collatz rules. What you get is this beautiful tree-like structure with all the branches eventually leading back to the root, which is the number 1.
So it's like a family tree of numbers, all descending from one.
Exactly. And it suggests that there might be some underlying organization or structure to this problem, even though the forward paths can seem chaotic.
Okay, so we've got these visualizations that provide some interesting insights.
Yeah.
But have mathematicians been able to come up with any actual supporting arguments or partial results for the Collatz conjecture?
Definitely. Apart from all the computational evidence, there's this probabilistic argument that a lot of people find intuitive. It goes like this. If you look at the odd numbers that show up in a Collatz sequence, on average, each one tends to be about 3/4 the size of the previous odd number.
So in a general sense, the odd numbers are shrinking as you go along.
Right. And that suggests that in the long run, the sequence should generally be decreasing, which makes it seem likely that it'll eventually hit 1. But it's important to note that this is just a heuristic argument, not a rigorous proof.
Right, because it relies on some assumptions about the randomness of the sequence that might not actually hold true.
Exactly. And it also doesn't definitively rule out the possibility of other cycles that don't involve 1. But it does provide some good intuitive support for the conjecture. Now, remember those stopping times we talked about earlier?
Yeah, the first time the sequence drops below the starting number and the total time it takes to get to 1.
Right. So in 1976, Riho-Terrace proved a really important result. He showed that almost every positive integer has a finite stopping time.
So for almost every starting number, the sequence will eventually dip below its starting point.
Exactly. And then, in 2019, Terence Tao, a real rock star in the math world, made a huge breakthrough. He showed that for almost all numbers, their Collatz orbits eventually descend below any slowly growing function of the starting point.
Wow, almost all sounds pretty promising.
It is, but there's a catch. These almost all results don't completely eliminate the possibility that there might be a small set of really weird numbers that don't follow the rule, and they also don't tell us anything about the total stopping time, only that the sequence will eventually go below some threshold.
So it's progress, but not the final word.
Right. And then there's also been work on establishing lower bounds. For example, Krasikov and Ligarius proved that for sufficiently large x, at least x to the power of 0.84 integers up to x will eventually reach 1. So we're getting closer to showing that a very large proportion of numbers behave as the conjecture predicts.
So we're narrowing the possibilities.
Exactly. But one of the big questions is, are there any other cycles besides the obvious 1 to 4 loop? Could a Collatz sequence get stuck in some other loop without ever hitting 1?
That would definitely be a problem for the conjecture.
It would. A cycle, in this context, would be a sequence of distinct positive integers that just repeats itself forever. The only one we know for sure is that short one, 1 to 4, 4 to 2, 2 back to 1.
So finding another cycle would disprove the Collatz conjecture.
Absolutely. And mathematicians have been working hard to rule out the possibility of other cycles. We now know that if any other cycle existed, it would have to be incredibly long. Current estimates put the minimum length of such a cycle at over 114 billion steps.
114 billion, that's a lot of steps.
It is. And remember that shortcut version of the function we talked about. If you're not using the shortcut, the minimum length of any other cycle would be even longer. Mathematicians have also looked at specific types of cycles called K-cycles. Yeah, these are cycles that you can break down into K-segments where the numbers are generally increasing and then K-segments where the numbers are generally decreasing. Think of it like going up a hill and then down a hill, K times. We know for sure that there are no 1 cycles other than the 1, 2, 4 loop and no 2 cycles. And more recently, researchers have shown that there are no K-cycles for values of K up to 91.
So any potential cycle would have to be pretty complex.
It would. And as computational power increases and these searches continue, it's possible that we'll be able to rule out even larger values of K. So while we haven't completely eliminated the possibility of other cycles, the constraints on them are getting tighter and tighter.
It's like we're closing in on them. And one of the interesting things about the Collatz conjecture is that mathematicians have come up with a lot of different ways to think about it, to reformulate it.
Oh yeah, there are some really fascinating ways to look at this problem. One is to think about it in reverse. So instead of starting with a number and seeing if it reaches 1, we start with 1 and try to reach all the other positive integers by reversing the Collatz
So it's
operations.
like running the process backward.
Exactly. If a number is even, to go back, you just multiply by 2. But if a number is odd, and it's of the form 3k plus 1, where k has to be an integer, then you can go back to k. This creates what's called the Collatz graph.
A graph of all the reverse connections.
Right. And the conjecture then becomes equivalent to saying that this Collatz graph is connected, meaning you can reach any positive integer starting from 1.
Okay, that's a really cool way to flip the perspective. And does that make it easier to solve?
Not necessarily easier to solve, but it does provide a different way to visualize the problem and might reveal some patterns or structures that aren't obvious when you look at it in the forward direction. There's another interesting reformulation that looks at the problem in base 2, the binary system.
Base 2, how does that work?
Well, in base 2, every number is represented using just zeros and ones. And if you look at the Collatz operation for odd numbers in base 2, it becomes a three-step process. First, you append a 1 to the right end of the binary representation. Second, you add this new binary number to the original binary number. And third, you remove all the trailing zeros from the result, which is the same as dividing by 2 repeatedly until you get an odd number.
It's like a little binary dance.
It is. And you keep doing this process until you're left with just a single 1, which in binary represents the number 1.
So it's the same Collatz rule, just expressed in the language of binary.
Exactly. And this binary perspective can be useful for analyzing the behavior of Collatz sequences and how their binary representations evolve. There's also a really elegant way to think about the Collatz conjecture using what are called parity sequences.
Parity sequences, what are those?
It's pretty simple. You take a Collatz sequence and just write down whether each number is even or odd. We can use 0 for even and 1 for odd. So you get a sequence of zeros and ones, which is the parity sequence.
So it's like a simplified representation of the Collatz sequence.
Exactly. And the cool thing is that the first k terms of this parity sequence uniquely identify the starting number modulo 2 raised to the power of k. Basically, it tells you something about the remainder when you divide the starting number by a power of 2.
So the pattern of even and odd numbers contains information about the original number.
It does, and this way of thinking about the problem has led to some interesting observations. For example, certain patterns in the parity sequence guarantee that the original number will eventually decrease, no matter what the exact value of the starting number is.
That's pretty cool. And there was something else I vaguely remember reading about, something about a connection between the Collatz conjecture and what are called tag systems.
Yes, that's right. You can actually reformulate the Collatz conjecture in terms of a special type of computational system known as a two-tag system. In these systems, you have strings of symbols that get transformed according to specific rules, and there's a particular two-tag system that behaves in a way that's equivalent to the Collatz conjecture.
So it's like translating the Collatz problem into a different computational language.
Exactly. And this connection is pretty profound because it links this seemingly pure math problem about numbers to the world of computation and the theoretical limits of what computers can do.
It's mind-blowing how interconnected different areas of math can be. And you mentioned earlier that mathematicians have also explored what happens when you apply the Collatz iteration to other types of numbers, not just positive integers.
Yeah, it's interesting to see how the behavior changes when you go beyond the realm of positive integers. For example, if you consider all integers, including negative numbers, you get some different cycles that involve those negative numbers. So it seems like the reach one behavior might be specific to positive integers.
So it's not a universal property of all numbers. What about rational numbers, fractions?
Well, you can extend the Collatz map to rational numbers that have an odd denominator. And there's this conjecture that states that every such rational number will eventually produce a repeating pattern of parities, the even-odd pattern we talked about earlier.
So cycles come into play again, but in a different way.
Right. And what's even more remarkable is that for any repeating sequence of parities, there's exactly one rational number that generates that specific parity cycle. It's a really neat connection. Mathematicians have also looked at the Collatz function in even more abstract number systems, like something called two-adic integers.
Two-adic integers. That sounds pretty advanced.
They are, but essentially they're a different way of thinking about numbers based on their divisibility by powers of 2. And it turns out the Collatz function can be extended to this two-adic world, and it actually behaves really nicely there. It has some cool properties, like being continuous and preserving a certain kind of measure.
So the Collatz function has its own life in these more abstract realms.
It does. And you can even push it further and extend it to the familiar real numbers and the complex numbers. But when you do that, you find that the behavior becomes much more complicated. You get fixed points, orbits that escape to infinity, and attracting cycles that don't involve the number one.
So the nice predictable behavior we see with positive integers breaks down when you go to these larger number systems.
It does. But even though the Collatz conjecture remains unsolved, mathematicians have developed some very clever tricks and techniques to make progress on it.
Like what kinds of tricks?
Well, one really important technique is based on what's called a time-space trade-off. The idea is that you can pre-calculate and store the results of taking a certain number of steps in the Collatz sequence based on the binary representation of the starting number.
So you're basically doing some calculations ahead of time to save time later on.
Exactly, and this can significantly speed up the process of checking large numbers. Then there's a whole set of techniques that exploit what are called modular restrictions. By looking at the behavior of Collatz sequences within certain residue classes, which are basically numbers that leave the same remainder when divided by some number, you can eliminate entire classes of numbers from the search for a counterexample.
So it's like narrowing down the search space by ruling out possibilities that can't work.
Exactly. And there's also the Syracuse function, which is a compressed version of the Collatz iteration that focuses specifically on odd integers.
We touched on that earlier, right?
We did. And this simplification can be helpful for certain types of analysis and computations. But despite all these clever techniques, the original Collatz conjecture, the one for positive integers, remains unsolved.
And we talked about some of the reasons why it might be so hard, like those undecidable generalizations and connections to computational complexity.
Right. The fact that even slightly generalized versions of the problem are undecidable suggests that the original Collatz conjecture might be touching on some really fundamental limits of what we can prove mathematically. It might be a problem that's beyond the reach of our current tools.
Okay, so let's take a step back and look at the big picture. We started with this seemingly simple rule: divide by 2 if even, multiply by 3, and add 1 if odd. And we've seen how this simple rule leads to all sorts of complexity and unanswered questions.
It's a reminder that even in mathematics, which we often think of as a realm of certainty, there are still mysteries to be unraveled.
And the Collatz conjecture is a perfect example of that. It's a problem that's easy to understand but incredibly difficult to solve, and it raises some profound questions about the nature of mathematics itself.
Absolutely.
So before we wrap up, we want to leave you with something to think about. Imagine for a moment that the Collatz conjecture is actually false. What would that mean? What kind of strange behavior would we be seeing in the numbers? Would there be these endless cycles or numbers that just keep growing forever? And what would that tell us about our understanding of numbers and arithmetic? It's a question that's worth pondering.
It definitely is. And if this deep dive has sparked your curiosity, we encourage you to explore this topic further. There are tons of resources out there, and who knows, maybe you'll be the one to finally crack the Collatz conjecture.
Thanks for joining us on this mathematical adventure. Until next time, keep those minds curious.